Welcome everyone to our Caltech Astronomy Stargazing lecture for the month of October. I'm Dr. Cameron Hummels. I'm a research astrophysicist at Caltech, and I will be our host for this evening's event. A brief schedule for what's going to happen tonight is I'll give a few announcements, and then I'll show roughly some of the things that you could see if you were to look up in the sky. Here in Pasadena, it's kind of dusk and there's still a bit of cloud, so it's not ideal stargazing conditions, but perhaps you're in a place with clearer skies tonight than we have here in Pasadena. And then I'll introduce our speaker for the evening, who will talk for about 30 minutes or so until probably about 7:40, 7:45. And with a really exciting talk. I'm really excited to hear it. And then following that, we will have a Q&A panel consisting of 4 members of our department, or including one former member of our department. And we'll answer questions on any topics that you have questions about related to space science, astronomy, astrophysics, or whatnot. We predict that there will probably be some questions about the Nobel Prize that was awarded this week in physics to 3 astrophysicists, actually, on basically the nature of black holes and black holes in the center of our galaxy. So it was a very exciting award and some really amazing science that's going on and has been going on for a couple of decades. So I encourage you guys to ask questions about all of that. So if this is your first time, we have these events once a month on a Friday night at 7:00 p.m. on the West Coast. And as I said, these are usually stargazing lectures. So when pre-pandemic, they were in person and we had telescopes set up on the fields adjacent to Caltech, and we would show people what was visible in the heavens, as well as you can do from LA metropolitan area with its light pollution. But and then we'd also have this kind of Q&A panel afterwards. So it's super fun. Our next one will be, I forget the exact date. I'll make an event in YouTube, in our YouTube channel. It's around the first week in November. And our speaker will be Dr. Katie Bauman, who you may remember was in the news in the last couple of years for being one of the leaders of the team who imaged the black hole in the supermassive black hole in a nearby cluster of galaxies, M87. And she's now a professor at Caltech, so she's going to talk to us presumably about black holes and imaging black holes. So it's going to be a very black hole centric next month or so. In addition to this series of events, we have something called Astronomy on Tap, which is, again, pre-pandemic was traditionally held in person in a bar, and it consisted of 2 informal 15-minute talks about some aspect of astronomy or space science while people would enjoy a beer. And very fun. Obviously, we're not doing it in person in a bar anymore. We're doing it streamed over YouTube Live, just like this event is occurring. But our next one of those will be a week and a half from now. It'll be on October 19th, which is a Monday night at 7:30 p.m. in Pacific time. And I don't yet know who's speaking. I'm trying to arrange who will be talking, but I can assure you they will be, I make sure we have great speakers and great topics. So stay tuned for what happens on that front. So as promised, I suggested I would show you guys, let's see if I can do this, show you guys what is up in the heavens right now. So this is a visualization tool that you should be able to see now called Stellarium. I usually show this at the beginning of all of our stargazing lectures. It's a free piece of software that you can download for Mac or Windows or Linux or what have you. And it gives you a view of what the sky looks like from any location on the surface of the Earth. And you can change to be at any arbitrary time in the future. And you can zoom in on different features. So this is a view of what the sky looks like from here in Pasadena right now. If you were to have no clouds in the sky. And as you can see in the southern part of the sky, so this is straight up above you at zenith, and in the southern part of the sky, you can see these two very bright objects, Jupiter and Saturn, and we can kind of zoom in on those guys. They look like very, very bright stars. And if you zoom in with, a decent pair of binoculars or a telescope, you should be able to see, maybe not to this resolution, but some of the banding on Jupiter, as well as these 4 dots that kind of are lined up. Those dots, which kind of look like stars, are actually moons that are orbiting around Jupiter, the 4 largest moons orbiting around Jupiter, called the Galilean moons, because Galileo was the first person to detect them by using a telescope about 400 years ago. Similarly, if you look at Saturn, you can pretty easily see that it has rings, maybe not, again, at this resolution, but you can see it almost looks like it has little ears at low resolution if you're looking through binoculars. So that's pretty cool. And those should be up for several hours. Trying to zoom out here. For several hours. So just like the sun or the moon, things rise in the east and then set in the west. So in a few hours, they will be setting in the west. But at that point, you'll find an object like Mars, which right now is right on the horizon. And again, is like a bright, it almost looks like a star, but it's very reddish. If you were to zoom in on that, you might be able to see some of the structure of Mars, but it looks very reddish, so it's quite distinct. And later in the night, Venus will be visible and quite bright. It'll rise around midnight or so, or maybe 1 in the morning. So that's about, I'm not going to get into too much detail on what's visible in the sky beyond those guys tonight, but yeah, let's get started for this evening. So Agnès, can you bring your video online and your microphone online? Oh, great. Nice.
Hi everyone.
Yeah, thanks for joining us tonight. So I would like to introduce our speaker, Dr. Agnès Ferté. She is a postdoctoral researcher at the Jet Propulsion Laboratory, the NASA Jet Propulsion Laboratory here in Pasadena, in cosmology. And she's also a member of the Dark Energy Survey collaboration, which tests non-standard cosmological models with its latest data. She's in particular interested in weak gravitational lensing to test laws of gravity, and she's still trying to prove Einstein wrong to this day, consistent with her talk title, trying to prove Einstein wrong. So Dr. Ferté is from the countryside near Reims in France, moved to Edinburgh in the UK for 3 years for her first postdoctoral position, followed by London for a few months, and then started at the Jet Propulsion Lab 2 years ago. And when not working, she can be found doing sport, reading, chess, borrowing her friend's dog, and hiking. And there's a link to her website in the description below. So yeah, I'm really excited to have you on here, Agnès. So do you want to start sharing your screen?
Yes. Okay. Is that working?
Yeah, that looks great. You're all set.
Okay, great. Thanks, Cameron. Thanks everyone for coming. So yes, today I hope to convince you that it's not dumb to try to prove Einstein wrong, and I will explain why and how we do this. So as Cameron said, I'm a postdoc in cosmology, and cosmology is a study of the universe as a whole. And I want to first start by explaining why we do cosmology and how we can do cosmology. So if you look at the sky with your eyes or telescope or binoculars, you see, you see stars like the sun, which I don't recommend looking with your eyes, but that's the kind of thing that you would see in the sky. You would see planets as well, as you can see this month, like Jupiter. You can see also other kind of objects like comets. So that's a picture that I took of the NEOWAS comets. So comets are like balls of ice and dust that are heated up by when they come close to the sun. I really hope that you got a chance to see it. It was really incredible, and it's a really rare event. We can also see with telescopes nebula, like remnants of dead stars. You can see dust blocking light from the stars. You can even see the effects of celestial bodies that don't emit any light. And that's, this movie is showing the orbits of stars that are modified by a very massive and compact object at the center of our galaxy, which is thought to be a black hole. So that's really showing the effect of a black hole. And this study has been awarded the Nobel Prize this week to Reinhard Genzel and Andrea Ghez. Andrea Ghez is actually the first woman ever to get the Nobel Prize in physics. And Roger Penrose also got the Nobel Prize for more theoretical work on black holes. You can also see, actually, even by eyes or with binoculars, galaxies like specifically Andromeda galaxy, which is the galaxy closest to us. So what I want to show here is that actually, like, the sky is very diverse. You have planets, galaxies, those nebulas, etc. And it's hard to understand why it's possible that we can say anything general about the universe by being so different. So if you take a step back, and I mean a huge step back, then you start seeing this. So this is an image taken by several telescopes showing many galaxies, far away galaxies. And so that's kind of like the scales that we're talking about in cosmology. We have to have new kind of units. So we don't talk in miles or in light years, we talk in parsec. So 1 parsec is 19 trillion miles. And we don't even talk in parsec, we talk in millions or billions of parsecs. So that's the kind of scales that we are thinking about. And when you are considering just large scales in the universe, we set some principle, and from there we can infer a lot of information about the universe. And 2 of these principles are, first, the universe looks actually quite similar wherever you look and whichever direction you look in the sky. Kind of like in this picture, in the background, you see like galaxies, you just see galaxies, and like there's nothing really specific. You can't really say something very specific. It's kind of looks similar if you look like on the left side of the picture or the right side. And the other principle is that we don't have a special place in the universe. We are in like a very common planet around a very common sun, in a very common galaxy, in a very common cluster, etc. So from those principles, that's a starting point for cosmology. Then the thing that's very important, one of the fundamentals of cosmology, is that at these scales, the only force that matters is gravitation. So gravitation is what keeps your feet on the floor, what makes things fall, what makes the Earth go around the sun, the moon go around the Earth. It's what keeps all the stars together in galaxies. And in cosmology, gravitation is described by the theory of Einstein of general relativity. So Einstein came up with this theory around a century ago. And that was really a revolution because he proposed a new way of considering gravitation. So the first thing is that actually you can't think about space and time separately. You have to think about space and time together, and they're very intertwined together. So we have space-time that we often image as like a sheet, like a grid, like here in this video. And then the idea of general relativity is that a mass will curve this space-time, this kind of grid, and things will just kind of follow, they will just try to follow like a straight line in this dip, and will just like be deviated by this mass. Like the Earth here is like staying like in this dip, going around the Earth. So this movie is a representation made by a French YouTuber, which you can check out the video at this link. So one of the major equation in general relativity is to say that curving space, like having matter in space-time will curve space-time, and that's what gravity is. And actually, this representation can be a bit misleading because we're actually living, in three dimension. So there is actually in this YouTube video, I recommend you check it out if you want to know more, but that's a representation in 3 dimension. So that's can actually in 4 dimension with time. So that can help to image what that means. Okay, so from this principle and adding general relativity as a theory of gravity, people at the beginning of the 20th century figured out that the universe must be expanding. And that's kind of like a weird concept. And actually that's the thing that made me want to do cosmology, is like when I've been told the first time that the universe is expanding, I was like, what? What does it mean? And so this image is kind of to try to represent what it means, with this balloon inflating with time, and the galaxies on this balloon. So it would be like galaxies in space-time. And the balloon is expanding, which makes the galaxies getting further and further away from each other, just because the balloon is getting bigger. So yeah, the balloon represents space-time, but you have to think about it like in 3 dimensions. It's not like just a 2D thing that grows. It's like everywhere the universe is expanding. And as often in science, if you have a theory, you have to validate it with observation. You have to verify that you observe something like what you have predicted with your theory. So also at the beginning of the 20th century, we had first Henrietta Leavitt, who figured out that you can estimate distance to objects because she measured the brightness of stars that have a variable. So if you measure this variability, you can infer the distance of these objects. So her work made us be able to measure distances to far away objects. Then we have Vesto Slipher, who was the first to discover that the light coming from galaxy is actually stretched by this expansion, and that's what we call redshift. And then Edwin Hubble, and with also Humanson, a person we don't talk that much about in cosmology, but he participated with Hubble to his observation. They put all of that together, they made observation, and they show indeed that the universe is expanding. Like the galaxies that are further away from us are getting further away faster from us. So Edwin Hubble actually used the telescope, the 100-inch telescope at the Mount Wilson Observatory, just here in Pasadena. So when I moved here, I was really like waiting for checking this telescope because it's like very iconic in cosmology. It's really one of the bases. That's where really the universe expansion was discovered. And here I'm just showing a picture from the webcam from the Mount Wilson Observatory just earlier this year, like just a month ago, because the observatory was surrounded by the Bobcat fire. But thankfully, thanks to fire management and firefighters, they managed to save the observatory. So after the pandemic and everything, once we can go there safely, I recommend you check it out. It's really, really like very interesting to visit, and you have like a wonderful view on LA and the LA area. So that was really kind of the beginning of cosmology, having this universe that is expanding. So that's an image that we often use just to show that the universe has been expanding since the Big Bang 13 billion years ago. So that's like a representation of just the universe expanding with time until now. The thing is that if the universe was mainly made of matter, then because matter, like everything, like matter that makes us, like everything around us, this would have a gravitational effect, and it would kind of like counterbalance the expansion, because you have the expansion, but then gravitation is like attractive, so it would kind of like slow down the expansion. And a bit more than 20 years ago, two different teams actually discovered that exactly the contrary happens. Instead of like slowing down, the expansion is accelerating. So that means that galaxies are getting away faster and faster with time from each other. So this work was kind of like built on the pioneer work from Henrietta Leavitt, where they measured supernovae. So supernovae are the explosion of stars at the end of their life. And this phenomenon is really energetic. Actually, it can be as bright as an entire galaxy. And the thing is that those supernovae, you can estimate their distance very well, because it's actually a nightmare to measure distance in an expanding universe. It's like really complicated. So you need this kind of ways to measure distance and then measure the expansion. So that's what's shown here on the top right. That's like a pixelized picture of like a galaxy, and then one day there is nothing. The next day there is this bit popping up. So that's the supernovae. And they measured plenty of them and discovered that the universe expansion is actually accelerating. Here, this little movie is just trying to show you what it means, like to have an accelerating expansion. So those circles is to just represent, like galaxies. If they just had the effect of the expansion, if there is no acceleration, that's how they would get away from each other with time. And if you have an accelerating expansion, that's what happens. They get away from each other, but like faster and faster. So it's like a strong phenomenon. So so we said that if the universe is made mainly of matter, the expansion can be accelerating. So what we say in cosmology is actually most of the universe is made of dark energy. Dark energy is this thing that would cause the expansion to accelerate. It's a very weird kind of like fluid, like energy, like we don't know anything that looks like that. Maybe a way to like a good image is like if you put like water in a glass, let's say, and so you have a certain level of water in this glass. And if the glass expands, like if the glass is just bigger, then the level of water would just get smaller, right? Just because you have more volume, so you just have you have the impression you have less. It's just less high. But dark energy, if you make the glass bigger, you have like the same level of dark energy. Like it doesn't dilute with the expansion of the universe. And that's like very weird, and we don't really know what it is. But the thing is that it really explains having dark energy in our equations for the universe. You explain very well the observation. But still, like the point of my research is maybe it's not dark energy. Maybe one of our assumptions in cosmology is actually wrong. And in particular, maybe the theory of gravity, general relativity, is wrong on cosmic scale when we look at distances, big distances in cosmology. So that's a goal of my research. So for that, it's one thing you can do is to say, okay, we just like matter reacts, like attracts matter through gravity. So if you study the evolution of matter in the universe, then you can you can infer information about the laws of gravity. You can test the laws of gravity. But there is one tiny problem. It's actually even weirder. Most of the matter in the universe is actually something that we don't know what it is either. So this image of the iceberg is to say that it's like we can see with our eyes, with our telescope, just normal matter, which is like the tip of the iceberg. But then there is also dark matter, which represents actually 85% of matter is dark matter, which is matter that doesn't emit any light at all. But we can see its effect gravitationally. So what we can see is galaxies, like here on the top right. But if we could see dark matter, that's what we would see here in the bottom right. Like we would see filaments in purple, and in yellow we would see like these clusters, like this clump of dark matter. We would see voids like in black here. So that's what we call the cosmic web. So that's actually how the universe would look like if we could see dark matter. So that's what we want to do. We want to understand, to measure the evolution of this cosmic web with time to test gravity, because the evolution of this cosmic web follows the laws of gravity. But because we can't observe dark matter directly, we have to find other way to measure, to observe it. And so in my research, the phenomenon that I use is lensing. So here I'm showing this movie that I made yesterday with like I just drew a grid with approximately parallel and perpendicular line. And if I put a lens in front between this like drawing and my camera, then I see that the lines are not parallel anymore, like they are curves. And that's because when the light goes through the lens, it gets distorted. And so that would distort the image that we see. Okay. The thing is that following general relativity, the exact same thing happens with matter in the universe, because as we said before, a mass will distort space-time, and the light coming from, for instance, from a star, it wants to go straight, like in a straight line. But because of this curvature, it will follow the space-time and will be curved. So that's what we call gravitational lensing. So what we use actually in cosmology is weak gravitational lensing. So when we observe faraway galaxy, if there was nothing between us and these faraway galaxies, we would just measure like their real shape, like we would see their image as they are like normally, as if we were close to them. But because there is matter between us and those faraway galaxies, this matter will curve spacetime and will then deviate the light coming from these galaxies. And in the same way, this lens was modifying the drawing of the grid. This dark matter structure will distort the image of these galaxies. So what we observe is the image of galaxies that are being distorted by this cosmic web, those dark matter structures between us and faraway galaxies. So that's a very powerful phenomenon to explore dark matter in our universe, including dark matter. So by measuring weak lensing, we infer the evolution of dark matter structure in our universe, and then therefore we can infer information about laws of gravity. But one of the problems, because there is always a problem in cosmology, is that this phenomenon is actually very, very weak. And we actually need to measure thousands, millions of galaxies to detect any signal. So that's just to show you what I need to do my job. And I will explain a bit what all of this means. Just this type of tea bags is just because I worked on my research during the day, and then during the night, I prepare talks or I apply to my job for next year. So yeah, it's busy life, but very exciting. So the first thing is that to do this observation of weak lensing, I told you we need many galaxies. So I joined a collaboration 4 years ago that's called the Dark Energy Survey collaboration. So the Dark Energy Survey was actually, people thought about it many years ago. And it imaged the sky for 6 years using the Blanco 4-meter telescope at an observatory in Chile, a bit north of Santiago, near La Serena. So this survey took place between 2013 and 2019. So the Blanco 4-meter is inside this dome here. And this is a view from my bedroom when I had the chance to participate to the observation. So I went through the equivalent of 2 weeks there. So it was really incredible, to be there. It's at the top of a mountain. It's very calm. It's really like a very different life because you live by night, you sleep by day. And you can just enjoy the night sky, which is incredible because it's in the southern hemisphere. So we see very different things from here. For instance, you can see the Magellanic Clouds here. That really looks like clouds, but they're actually like clusters of stars nearby. So yeah, so this is just showing a picture of like the dome from actually just outside my bedroom at the observatory. So these are these are images of galaxies taken by the Dark Energy Survey. That's really beautiful, but that's actually not what we are interested in at all, because those are like close by galaxies, they're actually big, and there are not that many of them. What we want is to really image a lot of galaxies, and for that we need big cameras. So that's the camera that we had set up on the telescope, the Blanco 4-meter telescope. It's made of CCDs, if you know what this is. It has a lot of pixels. Actually, it's the equivalent of 100 iPhones, the number of pixels. And that's a typical image that we get. With all the white dots here are galaxies, actually. And that's what we're going to measure. We're going to measure their shape, to measure the effect of weak gravitational lensing. So that's just a picture to show you here on the left. That's when we started the night of observation. Actually, that's like basically at the end of the day. We opened the dome before the night, actually, to have the temperature setting being equal inside the dome and outside. And here is the mirror of the telescope, so 4-meter mirror. And here is inside here is the camera. So the mirror is collecting the light and sending it into the camera. This is me, probably very tired because I didn't sleep like much, I guess, because this, you don't sleep much, let's say, when you do observations. With my colleague, Rachana Batadekar, we took this picture with the camera here in the background. So yeah, during the night, we made sure that the telescope was working fine with like all of these monitors. But actually, the thing is that it was pretty automatized. So I had a lot of time to watch Netflix in the meantime. But it was such a great experience to go there. And I was very lucky to participate to observation because not every cosmologist has the opportunity to do that. Okay, so that's for the observation. And the thing is, like, why do we need sunscreen? It's because, as I said before, we need to actually be at the top of a mountain to take very precise images of galaxies, because afterwards we want to measure their shape and different properties. So here is just showing the UV radiation index, like it's from a scale to 1 to 11, and it's 11, and it's basically 11 every day. So 11 is the max. So every time you go out, you have to wear sunscreen. yeah, so it's higher up, so there is less turbulence in the sky, and you have more stable images. So that's why we often put telescope at the top of mountains. So the thing is that to go from these images to actually saying something about the universe, we need many, many, many people. And the Dark Energy Survey collaboration is made of more than 400 scientists over 7 countries. And we need to coordinate all of our work together. And that's why we use Zoom. We have regular telecon. And we also use Slack to message each other on a very regular basis, to ask questions or to share what we're doing and get input from people. We also meet usually before the pandemic. We used to meet twice a year. Actually, this was a picture of the meeting in Brazil, which I didn't go to, but it looked really fun. So yeah, so that's how we do our research now. We, instead of going somewhere, we have meetings on Zoom, and a lot of messaging on Slack. And actually, earlier this week, I computed the number of the time that I spent sending messaging on Slack in the Dark Energy Survey collaboration since I joined in 2016. And I spent like approximately 10 days sending messages on Slack, which is a lot, but also that's the way we do our research. So that's part of the job. So the main idea at the end is that we have this data, this observation of this image of the galaxies. And from them, we will extract this weak lensing signal. And then the idea is that we compare the signal to what we predict theoretically. So that's where, that's most of my work, is to do this like more theoretical part, is to predict what the weak lensing signal we expect in general relativity, or in other theories of gravity. So what we call often modified gravity. So for this, actually, what I do all day long is to code. I use a lot of numerical computation, because we need big codes to go from one theory of gravity to what the weak lensing signal would look like. And also from time to time, I need to read books to verify some formula, take notes, etc. So yeah, that's the core of our analysis, is to have this data and to compare them with our theory. This way we can test our theory describe the universe well. And to do this numerical computation, we actually need supercomputers. So supercomputers are like massive, like really massive computers. So I'm using I'm especially using the NERSC supercomputer, which is in Berkeley. In particular, I'm using the Cori system at NERSC, and that has 70,000 processors. And in my laptop, for instance, I have like maybe like 16 processors. So it's like a very, very powerful, and like a lot of people are using this to run simulations or analysis. So I was very happy to see this in real life, and those are my picture, because I visited 2 years ago. And I was very excited because I used it for years, actually, since the beginning of my PhD. I was using a system at NERSC. And when I use it, I just kind of like send a code to the supercomputer, and the supercomputer does like all the computation. And then like I just take the output and analyze the output. So there is like nothing, we never like physically go there or whatever. So that's why it was kind of like very exciting to actually see it in real life. Okay, so doing like this whole analysis, comparing the data to the theory, then we get our results. We can test if actually Einstein's theory of gravity is correct or not. So once we have our results, so that's part of the scientific journey, we put that in the form of a scientific paper that we then submit to a scientific journal. And then hopefully they publish it, and we can share that to people. Actually, for the publication to happen, this has to be like the papers has to be checked by other colleagues, like other scientists. It's peer reviewed, which is one of the main thing in science, is that our analysis is checked by other people. So I want to show you one of the figure, like one of the plots that we produced in one of our paper to test the laws of gravity. And it's okay if you don't understand all the details, but I just wanted to show you what it means, like to have results on testing laws of gravity. So basically here, the idea is that we are summarizing the effects of changing the laws of gravity on weak lensing by just two numbers, two parameters. And if these two parameters, we measure them to be 0 when we observe our galaxies, like the weak lensing of the galaxies we observe, then that means that Einstein's theory of gravity is actually, it seems to be working fine on cosmological scale. It's still consistent. But if we measure something that's very different from 0, that means actually this theory of gravity might not be the correct one. And what this plot shows is that the colored area is gives you where the values of these numbers. We can talk more about this in the questions, but so I guess here the point is that those two numbers are 0 and 0, so 0 here and 0 here, are inside those colored area, which means that Einstein's theory of gravity is still holding on cosmological scales when we use the dark energy survey data. So that was actually using only the first year of observation from the dark energy survey. But I told you, we observed the sky for 6 years. And actually, that's what we are working really hard on right now, is to process the 3 years of observation, which will give a more precise measurements of these weak lensing effects. And we will test more precisely the laws of gravity. And then we will do the analysis using the full survey. But then let's think about, in a few years when we will have finished this analysis. Then we have even bigger telescopes that are planned and that are already being built right now. So one of them is Vera Rubin Observatory. So now this telescope will be 8-meter telescope, and the camera will be like is the biggest camera ever done. And it has been put together at SLAC near Stanford. And that will, we will be able to have even better and more precise measurements of weak gravitational lensing, and then test even better laws of gravity. So here, this picture is actually the first, one of the first pictures that they took with this camera. But of course, they did that in their lab when they put the camera all together. They did a test, like taking a picture. And this is an image of Vera Rubin. So Vera Rubin was a scientist who was one of the first ones to realize that there has to be dark matter, because she observed that the galaxies rotate faster than expected, which means that there must be more matter than we see. And here I just want to note that it's very exciting to see that people have named a big observatory that will be very important in the coming decades after a woman, especially because women in science, and especially women from minorities, are really underrepresented in science. So it's a very big step, you know, to give them more visibility and just to add them, to honor their memory, basically, by naming things after them. So yeah, this picture of Vera Rubin is actually one of the largest picture ever done, because that's taken with the largest camera. They did also other tests taking pictures of the head of a Romanesco, and you can check out online. It's very interesting. Another thing is that if you wanted to show this image, you would need like 400 4K TV. That's how like how many pixels and how many like detectors there are in the camera. So that's very exciting. We will have like very beautiful images of galaxies and very great measurements of weekending. So yes, that's I guess that's the end. So is it dark energy that is causing the universe, the expansion of the acceleration of the expansion, or is it that the theory of general relativity is actually not right when we consider cosmological scales? So for now, with the data that we have, Einstein theory of gravity still holds, but we will see in the future with better measurements what it will say. And this picture here in the background, it's a picture I took from the observatory in Chile, so where the Blanco 4-meter telescope is. And here in the distance, you can see actually the Vera Rubin Observatory starting to be built, because it's just like in another mountain nearby. So that's just also to say that there is great science in the horizon. Thanks everyone for joining and for listening.
Excellent. Thank you so much, Agnès. That was wonderful. All right, so as promised, we will go straight into our Q&A panel. So I'd like our other panelists, Mia de los Reyes and Dr. Leo Stein, to unmute and turn your video on so that everybody can see our faces. Welcome, guys. So yeah, members of the audience, we encourage you to ask questions in the YouTube description. But before we do that, so we know who Agnès is because she just gave this wonderful presentation about the Dark Energy Survey and her research with it. Briefly, we'll go through the other three panelists and introduce ourselves and what sort of science we do. And then we'll start asking questions of you guys. We'll try and answer the questions of you guys. Hopefully we won't be asking questions of you guys. So I'm Dr. Cameron Hummels. I do computational modeling of how galaxies form and evolve over cosmic timescales. So since the Big Bang to present. And the reason for that is when we look up in the sky and we see galaxies, the timescales over which they form and evolve are very, very, very long compared to what timescales we as humans experience. So, you know, an average human lifetime is 80, 70 years, something like that. Whereas a galaxy, to make one full revolution, like for the Milky Way galaxy, which is kind of a disk, to make one full revolution takes about 250 million years. So obviously when we look up at a different galaxy, if we take a picture today and compare it to a picture that was taken 100 years ago by Edwin Hubble, for instance, it's the same picture for the most part. There's very little change that has occurred on that short of a timescale for the galaxy. So computer simulations allow us to speed up time in the simulations to see how they move over much longer timescales and better understand why they behave the way they do. Anyway, Mia, would you like to introduce yourself and what you work on?
Sure. Hi, everyone. My name is Mia de los Reyes. I'm a fourth-year grad student in astronomy, and I'm an observer. So I take data from optical telescopes mostly, and I try to study the chemical composition and evolution of low mass galaxies that are pretty close to the Milky Way. So the idea is that the Milky Way was built up from a lot of these very small systems, like small galaxies merging together over time. And so by understanding these really small building blocks, we can understand a lot about galaxy evolution and formation. So that's what I do. It's great to be here. Thanks so much for having me.
Excellent. Thank you, Mia. Leo, would you like to introduce yourself?
Sure. Hi, I'm Leo Stein. I was at Caltech doing a postdoc for 3 years, and many years ago I was an undergrad there. So that's why Cameron let me crash tonight. But I'm an assistant professor at the University of Mississippi now, and my main focus of research is well, I'm a theorist. I want to understand other ways of studying Einstein's theory of relativity. So similar to what Agnès was talking about, but my focus is, instead of on the cosmological scales, on the largest scales in the universe, I'm interested on the scales of black holes and black holes going around each other, making gravitational waves. So mainly I'm interested in how those kinds of systems can tell us anything new about gravity, whether it's different from Einstein's theory of relativity.
Excellent. Yeah, I brought Leo back in as our heavy hitter black hole speaker, since he would always be very helpful at our in-person events when he was still a postdoc in the department, at helping address questions about black holes. And given the whole nature of the Nobel Prize being associated with black holes, it seemed appropriate to bring him back on. Not that Mia, Agnès, and I can't handle it, but it's good to have a black hole hardcore theorist on stage. So okay, so let's try to let's hit some of the questions that you guys have been asking. There were a few that were raised during the presentation itself. So what are the other, so this is related, there have been a couple of questions about a specific graph that was shown in Agnès' presentation. What are the other dark regions in that graph? For example, the blue region below it. Agnès, do you want to bring that slide back up and share your screen and maybe discuss that a little bit more?
Yes. Wow, that's like really top science, people. That's a great question. Okay, I don't know if that's working. Okay. Yes. Very good question. Like, why are there like 3 different types of colors? So actually, one thing that we do as well in cosmology, so we compare between different type of different way of observing the universe. So here in blue, that's the area that corresponds to the data from the dark energy survey weak lensing data. In yellow, that's another type of experiments that I observed, those supernovae I was telling you about, those star exploding. Also data from the primordial light of the universe, the cosmic microwave background, and another type of data, yeah, for people who know what that is, bionic acoustic oscillation, but it's another type of way to measure distance in the universe. So that's what these data tell us. And then, so this way we can compare between different ways of observing the universe. Like, this way we can check if they say the same thing, and then we can combine everything together and then get, like, you know, very even more precise measurements of these two numbers, these 2 parameters to test gravity. And so that's the red thing. That's when we combine all of this data that we have all together.
You're still muted, Cameron.
Thank you, Leo. Too many windows. I'm sure everyone in this day and age understands that issue. Thank you, Agnès. That was wonderful. Yeah. And good questions from the audience, catching these pretty high level issues. Let's see. Ooh, I like this one. Can any of us explain what is a pair instability supernova and why does it not leave a stellar remnant behind? Anybody? I could talk about this. I think all of us could probably talk about this. Leo says no.
You got this, Cameron.
Okay, you'll correct me where I mess up, Mia. Okay, so there are lots of different kinds of supernova in the universe. Supernova generally occur at the end of a star's life when it becomes, well, never mind. There's lots of different kinds of supernova. Core collapse supernova are ones where you have a really massive star and it runs out of a pressure source in the interior because gravity is always trying to collapse massive things to be denser and smaller, right? But in most stars, well, in all stars, you have some form of pressure in the interior pushing back on that gravity that keeps it in somewhat of a stable configuration. And in pair instability supernovae, yeah, you guys will have to make sure I'm sticking to what I know here. The star is, I believe these tend to occur with supermassive stars and what like potentially POP3, so first generation of stars that are very massive, on the order of hundreds of solar masses potentially. And the core reaches a point where it is unable to produce heavier elements. So, and in producing heavier elements through nuclear fusion, it's releasing energy that's keeping the outer layers of the star propped up. Actually, it can no longer do so, so the star starts to collapse. But, oh wait, but before you get there, when you're producing heavy elements, yeah, I'm totally messing this up. When you're producing heavier elements, you're also producing photons, very energetic rays of light, like X-rays and gamma rays that are propagating out, and they're providing that pressure source from the interior to prevent the overlying layers from collapsing. But eventually they become so energetic, these photons, that the photons actually produce pairs of particles, a particle and an anti-particle, and yeah. Oh shoot, this is like a qual question. Who wants to chime in? Mia, you look like you're ready to kick my butt and set me straight. Are you ready to kick my butt and set me straight?
No, honestly, I don't know that much more beyond what you've been saying. I mean, I think the general idea is it has to be within a certain mass range. I think it's between like 100 and 130 times the mass of the sun. And it does have to be super low metallicity. So this is why one of the reasons why pair instability supernovae would be really interesting if we could find evidence of it happening, conclusive evidence of a pair instability supernova, is because there's a lot of work trying to look for really low metallicity. So the very first generation of stars, like Cameron said, stars that haven't, because as stars live and they die, they produce heavier and heavier elements. And so the very first generation of stars hasn't had time to do any of that yet. There are no heavy elements for them to incorporate when they get formed. And so looking for those first generation of stars is sort of the holy grail in a lot of fields of stellar and galactic astronomy. And so this is one reason why looking for evidence of a pair instability supernova would be really interesting. I think the idea is that when the core begins to collapse, you produce a lot of really energetic particles called gamma rays. So just very energetic photons. And if you're in this magical 100 to 130 solar mass range, then the gamma rays are the right energy to cause, as Cameron says, these positron and electron pairs. So an electron and anti-electron, which then annihilate and cause huge amounts. It creates a lot of energy, and it also destroys everything in the star. So if you have enough of these really energetic electron-positron annihilations, then everything in the star gets destroyed. So that's why there's no stellar remnant.
I think what I remember about the I mean, I might misremember, but about the pair production is that, you have these photons are providing a lot of radiation pressure, and you need all of that radiation pressure to keep all these upper layers of the star from collapsing down.
Yeah.
But once these photons get enough energy, so above 2 times 512 keV, so 512 keV in particle physicist units is how much an electron weighs. So 2 times that, so it's to make an electron and a positron. Once a bunch of photons start making positrons and electrons, instead of like pushing on the rest of the material to support it, they're just making all of these new particles. And those particles aren't moving fast because a bunch of the kinetic energy of the photons that is pushing is instead in the rest energy of the particles. And so these non-relativistic particles, the positrons and electrons, don't provide enough pressure to support all of the upper layers of the stars. So once you cross this threshold, suddenly all of your pressure support starts going into making extra particles instead of holding up. And that's why it starts collapsing.
That's right. Okay. I think we all had a part in that solution. So yeah, exactly. So then it collapses and then boom, it's a big explosion and there's no leftover bits of the star, I think. Anybody else want to add anything? Okay. Okay, that was good. We pieced that together. We all passed the qual together. Good work, team. Okay, so another question. Lots of good questions here. How about, given the recent LIGO discovery of a black hole merger resulting in a previously thought impossible medium-sized black hole, could it be that there are a lot more black holes than we previously thought, and that dark matter is all of those black holes? Ooh, okay, this is good because this touches on a few different areas that we're dealing with. So yes, the question relates to a discovery, a paper that came out in the last month or two from the LIGO consortium, the Gravitational Wave Detection Consortium that was awarded the Nobel Prize in 2017. And the main result of the paper was that there were 2 black holes. I forget their exact masses. They were in the teens of solar masses. People, anybody? Teens of solar masses, and they were, or it was thought that they were teens of solar masses, and they merged together to be on the order of, I thought it was like a 40 solar mass black hole. Is this? I should look up the paper right now. Sorry, I don't have this off the tip of my
I think the person was asking about the very heavy event.
Well, that's what I'm talking about. Was it even heavier than 40? I thought it was in the less than 100 range.
I thought that it was heavier than that.
Oh. I know people kept citing it as the intermediate mass black hole range, which is kind of a stretch because it's not really, when I think of intermediate mass, I think of like much more than that, like hundreds.
I thought I remembered that the remnant like just broke 100, or at least the posterior distribution for how heavy was the remnant broke 100 solar masses. I think I remember somebody winning a bet about that.
Okay. Well, either way, the numbers aren't specifically relevant for this discussion. The 2 black holes that were on the order of many times the mass of the sun merged together and formed an intermediate mass black hole that was thought previously not to be favored by theoretical models, somewhere in the order of 100 solar masses, something like that. And oh, Leo, you're saying...
I just looked it up. Yeah. Okay. The like most probable masses of the 2 individual black holes before they merged was like close to 60 solar masses and close to 80 solar masses.
Okay.
So they merged together to make something that's close to 140 solar masses. But the numbers, because the signal is not like super duper loud, it's like pretty loud, but so they're confident about the measurement. but not so loud that they have a very precise measurement of the masses.
Right. And so the question is, given that the theoretical models didn't really account for the presence of these intermediate mass black holes in the past, is it possible that there's a whole bunch of these things out there, since we didn't think there were any and we just found one, and maybe that the presence of those, tying back to, you know, the topic of the talk and such, could be responsible for the unseen mass that might be out there, dark matter or something like that?
Yes. So yes, that's something that's kind of like, you think if you look at dark matter, you're like, yes, something that doesn't emit light, that's very massive. That's, yeah, black hole totally could explain that. So there are a lot of studies that were done in like our, like observing stars in our own galaxies, trying to look for lensing effects again. So like the stars being, the light coming from stars being deviated by like black hole. That's what people are looking for. And thanks to that, they can place limits on the amount of black holes, or the amount of dark compact objects, at least, that could produce lensing. And I thought people said that you can't explain all of dark matter with black holes. Yeah, only partly.
Yeah, I think I remember there's, you know, these things are very subtle. So it's hard to test these models. And the one kind of thing that I know has been ruled out was, you know, what if there were primordial black holes that were all of the same mass that were supposed to make up dark matter? Well, then, you know, there would have been a certain number of signals of this certain mass range. So that would be inconsistent. It's not consistent for all of them to be at one mass, but it's harder to constrain if there was like a spread out distribution of different masses.
Yeah, I don't know. Do other people have anything more to add on this particular question? Oh, thank you for the link. Thank you for the link, Leo. Trying to do too many things. Too many things. Okay. Okay, next question. How will the newly launched Starlink and other satellites affect the astronomical measurements? Can you cancel their effects through some sort of computational means? So I assume the astronomical measurements is referring to the astronomical measurements being done and that were talked about by Agnès. But I guess this could also be globally. Can we account for you know, correcting for the passage of these Starlink or mega constellations that are going to be overhead? So I guess specifically to the work that you were talking about, Agnès, do you want to, because I think that's a very specific way of.
Yeah, so actually for exactly my work, I mean, I don't know all the details, but I just thought I would show you a picture, if I can just share my screen. Just very quickly here. So that's, you might recognize this image. It looks a lot like the image that I was showing you. And that's because that's the DECAM camera, the camera that was used for the dark energy survey, and that's being used for another type of survey right now. And they took images, and that's all of these tricks here are the Starlink when after they were launched. So in this example, it definitely has a huge impact. But I think that was when the satellites were on their way like to like a bit higher orbits, and that's hopefully they would, and that then they would get dimmer and and hopefully not pollute too much. But totally, I mean, the thing is like, for instance, like planes, that we also have that in our images, but that we managed to like correct for this. But if we have tons of streak like this, then that starts to be a problem. But I don't know if anyone else has additional comments on that.
Sure. Yeah, I mean, so just for reference for people who aren't familiar with the whole idea, SpaceX and some other technology companies, with the lowering cost that it takes to launch things into space, are planning to launch a large number, on the order of thousands and tens of thousands, of small satellites into orbit around the Earth to do a variety of things. In the case of SpaceX and Starlink, that's kind of the most publicized and well known of these projects. I think right now the concrete plan, and you guys can correct me if I'm wrong, I'm sure a simple Google search will be able to correct me where I'm wrong, but it's on the order of like 10 or 15,000 satellites, and potentially even more than that. So it's a huge number of satellites just from SpaceX. In the case of Starlink, the SpaceX project, it's to provide global internet access. But other groups are doing global imaging, where you're looking down on the surface of the Earth with frequent intervals to be able to map out, you know, the progress of forest fires, or the effects of global warming, or the progress of storms, or spy on your neighbor. I don't know. There's all sorts of uses for this, but there's right now there's a huge growth in the planned numbers of satellites that are going to be in space. And of course, when something's in space, if this is your Earth and the sun is that light that's shining at me right now from where you guys are, and you have a satellite going around, so that this back side over here, not facing the camera, not facing you guys, is the night side. And if there's a satellite that's right here, it's visible from the night side, but it's also being illuminated by the sun directly. And so it's reflecting light back towards the night side. And the closer you are to the Earth, the less time you spend visible to the night side, but still illuminated by the sun. But you're very close to the surface of the Earth, so you're quite bright. Whereas the farther away you are, the dimmer you are, but also the longer you spend visible from the night side where you're actually illuminated. So it's a trade-off. And as Agnès was saying, early on with that image that was taken, those were when things were really close to the surface of the Earth, the satellites were. So they were quite bright, but you only saw them within an hour or so of dusk. Whereas when they get to higher and higher distances from the surface of the Earth, you'll see them later and later after dusk or before dawn. But hopefully they're fainter. But it is a major problem, and for the most part, the technology companies are kind of ignoring it and hoping that the technology will come up with some really good image reconstruction techniques to fix the problem. And I'm not convinced that that's a good solution. I think there needs to be pro-action on the case of the technology companies, whether it's Elon Musk sitting down and saying, let's really try and work to minimize the amount of scattered light that's coming off of our satellites, or Jeff Bezos to do the same with his planned projects, or whomever, to really come up with a conclusive way to mitigate this effect. Because it's not just an effect that's going to impact astronomers and astrophysicists who are trying to study the heavens, but it's an effect that's going to affect all of us. You know, you go to a dark sky site, I don't know, Death Valley or Joshua Tree, and now you've got tens or hundreds of these artificial lights streaming across the sky like an airplane. It's losing a natural resource. It's all of us losing a natural resource of being able to look up in the sky and just see the night sky instead of flashing lights all over the place, which kind of sucks.
And sometimes I think that maybe at some point people will do ads using the satellites, you know, like images in the sky, and I'm like, no, please, never.
Like Blade Runner. It's
yeah.
a frightening dystopia for a variety of reasons. So yeah, I don't know. Do you guys have other things to add on that? I don't mean to yap too much, but I tend to yap too much. Okay, so other questions. I keep losing my window. Black hole question. Fermions cannot be in the same state and in the same place, correct? Can this be used to find lower limits on the size of a singularity in a black hole? Kind of equivalent to radiation pressure. I'm not sure I just find lower limit the size of singularity in a black hole.
I think I know what the question, what the asker is trying to get at.
Okay.
I think it would be, it's really hard to speculate about this. This gets into the realm of trying to combine quantum mechanics and gravity, which has been a problem, you know, basically since general relativity came on the scene, because quantum mechanics already existed at that time. So yeah, people have been trying to understand how to combine quantum mechanics and general relativity since, I mean, maybe not right at 1915, but for sure in the early 1920s. Okay, so I can't speculate anything too precise, but I could just say general things, if that's okay. So I think nobody in physics really likes singularities. Just to connect this back to the Physics Nobel Prize that was awarded or announced earlier this week. That was one of the things that Roger Penrose contributed to understanding of black holes. There's this general question at the time, like there was a black hole solution known that had a singularity, and people didn't know if the singularity was just like because the black hole solution was assumed to just be perfectly spherically symmetrical. Because sometimes when you make these kind of simplifying assumptions to make the math easier, you get results that are not true in the general case. So people thought, okay, maybe that's just special because Karl Schwarzschild assumed that it was a perfect sphere. So Penrose asked, okay, what if we break the spherical symmetry? Because, you know, if a star collapses, a star's, you know, it's kind of blobby shape, it's not a perfect sphere. So it's not going to make a black hole that's a perfect sphere either. It's going to be spinning. So Penrose actually showed that the formation of singularities is generic in general relativity. It's not a special thing. It like typically happens. So, okay, general relativity just makes singularities. But most people who work on this theory don't really like singularities. That's where the theory breaks down. And one of the hopes is that having an understanding of quantum gravity, where you make gravity itself quantum mechanical, would get rid of this singularity. And the reason that you might suspect this to be the case is because when the closer and closer you get to the singularity, the smaller is the radius of curvature. So there's a natural length scale associated with how strongly is gravity curving things. That length scale is called the radius of curvature. And if that length scale gets down to this combination of units you can form called the Planck length, then something different should happen in the way that the theory works. Like we expect general relativity to work really well when length scales are long compared to this Planck length. But if the radius of curvature gets really close to the Planck length, then we think that you can no longer ignore quantum mechanical effects. So there's kind of a hope that adding quantum mechanics should hopefully get rid of singularities. And there are some, you know, arguments from various different models. None of this is like a consensus. There are different models that some things called like loop quantum gravity would smooth out these singularities, so you wouldn't have them anymore. I'll say that it's not really due to any type of fermion thing, because you know our understanding of gravity is that if you were to make it quantum mechanical, it would be like gravitons would be like bosons, like photons, or gluons. If you're a student who is going to be taking quantum field theory at some point in the future, then wait around for when you learn about spin, and this is a spin 2 particle, so that's an integer, and that means that it's a boson, not a fermion. But the idea is still that quantum mechanics is somehow supposed to get rid of these singularities, and there would be like a maximum upper limit on curvature, which is the same, which maybe is the same size as like, instead of having a singularity, there would just be a length scale of region where you get quantum mechanical effects that might be on the order of Planck length. All right, that's my hand waving for the day.
Okay, thank you, Leo. We have a question that is super relevant to Mia and Mia's science. Why do some ultra-faint dwarf galaxies like Reticulum 2 contain a higher proportion of metals than other similar type galaxies?
All right, so first let's break down this question. So a dwarf galaxy is just a really low mass galaxy. So lower mass, people define this in different ways, but generally the rule of thumb is if it's smaller than the Milky Way, which is on the order of 100 billion stars, then some people will consider anything smaller than that a dwarf galaxy, a low mass galaxy. Ultra faint dwarf galaxies are like the smallest of these small dwarf galaxies. So they're on the order of millions of stars compared to, billions for some of these other dwarf galaxies. And they all tend to have really low metallicity. So when we talk about metallicities, we're talking about the heavy element content of the galaxy. So in the early universe, there were no elements heavier than trace amounts of lithium, but it was hydrogen, mostly hydrogen, helium, and some amounts of lithium. And none of the other elements existed in the very early universe. And so stars had to be the things that made all of the heavier elements. And so astronomers call anything heavier than helium a metal, which makes it difficult to talk to chemists. Chemists don't like us for that reason. But when we talk about metallicity, we really mean we're talking about all of these other elements. So literally anything heavier than helium. And so these ultra-faint dwarf galaxies have extremely low metallicities. So the stars in them tend to have very low concentrations of these heavy elements. But there are a couple, like Reticulum 2, that still have, like, on average, they have roughly the same content of heavy elements, but the exact kinds of heavy elements they have are different. So different heavy elements are made in different ways. The carbon is in our bones, say, or in our cells, mostly came from not the same processes as the things that made, say, gold, which is much heavier. And so in particular, I think what this question is trying to get at, there's a dwarf galaxy called Reticulum 2, an ultra-faint dwarf galaxy called Reticulum 2, which has gotten some press because it has more of these extremely heavy elements, what we call R process elements. So R process elements are basically made if you take a lot of neutrons and throw them at an atom really fast. So R stands for rapid. If you throw the neutrons rapidly at elements, then you get these really massive elements like gold, I can't think of any off the top of my head. Gold is sort of the easiest one to think of, but there are several others that are considered R process elements.
Is it just like everything that's heavier than lead and nickel, or
no? So there's
some
also
of those also.
Yeah,
oh, okay.
So they make different patterns in what we call the nucleosynthetic table, with sort of like a periodic table, but for when you make nuclei and not atoms. And they have different patterns. So let me quickly look up some of the other R process elements. Thorium, uranium, like those are like some of the heaviest elements, but there are, gold is not quite so heavy, but it's still considered mostly an R process element. And so the reason that we think Reticulum 2 has such a high concentration of these R process elements is because we think there was an event that happened, what we call an R process event, that made a lot of, this is really circular logic, it sounds like, but we think it's a super rare event. And so this is really interesting for a lot of reasons, because the site of the R process, the thing that makes R process elements, has been pretty heavily debated in the last few years, especially as LIGO has discovered some indirect evidence follow-up from some of these gravitational wave events has showed that if you take two neutron stars and merge them together, you can get something called a kilonova. And the kilonova has shown some signs of making these R process elements. So this is really pointing towards neutron star mergers, the mergers of two really dense neutron stars, as one of the key sources for R process elements. And so we think a really rare event, maybe a neutron star merger, happened in Reticulum 2. And that's why it has so many more R process elements than a typical ultra faint dwarf galaxy. Sorry, that was a very long and detailed question when the answer was really just a rare event did it, and it was maybe a neutron star merger.
No, that was a good question and a good explanation. Thank you, Mia. Before we go any further, there was some misconceptions in the chat about one of the announcements that Agnès had said during her talk, and that was the announcement that Andrea Ghez, one of the 3 scientists who were awarded the Physics Nobel Prize this week, that Andrea Ghez was the 4th woman to receive the Nobel Prize in Physics. I think some people misunderstood Agnès' sophisticated French accent when she said first, said 4th, it came out as first, or they perceived first. But yeah, so Andrea is the first woman astrophysicist to receive the award, but she's the 4th woman any physics to receive the award in its 120-year history. So it's a pretty major accomplishment and very exciting. Okay, so let's go on to the next question. Well, actually, before we get there, I just want to announce the actual name, the actual award. So we've referenced the Nobel Prize in Physics, the announcement that occurred this week a few times, but I'm just going to read the official description that the award was made to the physicists that we've mentioned by the Nobel Committee. The Nobel Prize in Physics 2020 was divided. One half awarded to Roger Penrose, quote, for the discovery that black hole formation is a robust predictor of relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez, quote, for the discovery of a supermassive compact object at the center of our galaxy, unquote. So this is super exciting. I think many of us have had interactions with one or more of these people. Andrea Ghez is an alumna of Caltech. She was, I believe, a graduate student, or was she an undergrad? Do you guys know? She was an undergrad?
She did her PhD at Caltech. Okay. She did her undergrad at MIT.
Okay. And she's now a professor at UCLA. And Reinhard Genzel is German. He is the director of one of the Max Planck Institutes in Germany, outside of Munich. Although he's also a professor at UC Berkeley, so he's split between both places. He was at Caltech 6 months ago, right before the pandemic. I remember he came to one of Phil's group meetings, and he's great, super cool guy. I've never met Andrea. I've heard that she's wonderful. I mean, in addition to her science, she's just a really cool lady. Penrose, Roger Penrose, the Englishman, is quite old at this point. He collaborated a great deal.
I think he's 98.
Yeah,
is that how old
he's
he is?
Super old. I saw him speak 15 years ago, and he was like really old then.
89. Sorry, I got the numbers backwards. He's 89.
Yeah. He's just a bit of a polymath. I mean, he's done a huge amount of stuff across the board. I mean, not to dismiss Reinhard and Andrea, their work is formidable and amazing, but Penrose has done a huge amount of stuff in a variety of different areas of research, and the GR black hole stuff is an important part of that. But he's also done quasi-crystals and tilings of things. He's done. Now he's doing all this conformal cosmology stuff, which is questionable. I think there's a lot of pushback.
I think he was also interested in whether or not consciousness has a quantum mechanical origin in the brain, which is also not a consensus opinion among biologists or cognitive scientists.
Yeah, he's done a lot of interesting stuff on a lot of different topics, and not all of it has rendered, yeah, consensus amongst the groups who focus on that particular thing. But that's okay. That's how science is done. You know, you put out ideas and maybe they are right, or maybe they get rejected by other people who continue to look at this and know, you know, study different aspects of what you're proposing. So anyway, the science is very, very intriguing. And so just to bring everybody up to date on what's going on that front and why we're talking about black holes and such. How about, if gravity is the curvature of space-time by a massive object, then what is the force that curves space-time? Okay.
Should I say something? I don't know.
Oh, well,
yeah, go ahead.
I think it's a little bit of it's a little well, I think it's hard to speak about it in terms of forces. Force is, you know, a precise word that we use in physics for, you know, the rate of change of momentum. I guess what we really mean is like, I think the word that physicists would use is like, what is a source for gravity, or what couples to it, right? Because the same thing happens not just with gravity, but also with electromagnetism. Like charges generate electromagnetic fields. So, but if you were to ask the same question about the electromagnetic fields, then if we just replace the words, then it would be like saying, you know, if, what was the phrasing? You know, I guess I don't think that we would ask, what is the force that generates electromagnetic fields? I think we would usually say, you know, what is it that generates or sources electromagnetic fields? And I think maybe this is like a philosophy of physics question. Like, how do we interpret what the theory is saying? The theory literally just says that anything with a charge generates some electromagnetic field. And the same thing in Einstein's theory of relativity. Anything with mass or any type of energy or momentum or pressure, all of these things are part of the same type of quantity in general relativity. All of that stuff generates curvature. It sources curvature. We don't really talk about it as a force. I guess we don't really think about it as like matter pushing on space-time. You could kind of think about it like that, but I don't think about it as a push. But I don't know. I think I'm not equipped to talk about the philosophy of physics.
That's fair. We're physicists, not philosophers. Also, I want to apologize. It's come to my attention that my connection is not very good. Thank you, Comcast. Thank you, Spectrum. So I will give them an earful tomorrow, but I hope I'm not too choppy. I apologize for any choppiness on my end. Okay, so here's a question from a bit ago. I got interested in telescopes. Are space telescopes useful to study gravitational lensing, like what Agnès was discussing?
Yeah, so for weak gravitational lensing, totally, they are very interesting because so one thing is, if you build your telescope on the ground, on Earth, one thing that's useful is that you can make like really big mirrors, because you can just, like take your mirror and put them there. If you go to space, then you have to sense a lot of things, like all the material that's heavy, that takes a lot of fuel, etc. So yeah, one advantage of like having telescope on the ground is that you can really have big telescopes, and you can also repair them easily. You just go there and you do your repair if there is any problem. But one of the major problem, for instance, with gravitational lensing is the atmosphere, because the atmosphere will also affect the shape of the galaxies that we image, and even in general, you know, like in astronomy, the atmosphere will make our measurements less precise. So yes, there is a big advantage of going to space. Although it's more expensive, it takes more time to build as well, because you have to make sure that everything will work fine. Because once you launch the telescope, you can go repair it. I mean, except for Hubble, actually, people have repaired it. But like for cosmology experiments, we actually send them quite far from Earth, so we can't really go there to repair. And so there's really a big advantage to go to space, but it costs a lot. And actually, in the coming decades, we will have two different space telescopes who will do measurements with gravitational lensing. So the one that will come first in time is the European ESA Euclid telescope. So that will be launched in a few years, I think. And it will observe a really large part of the sky and observe galaxies and observe also measure the spectra as well. Actually, yeah, part of it. And later on, at the end of this decade, we will have the Nancy Grace Roman telescope. So another experiment named after a woman, Nancy Grace Roman, who was very important in the history of NASA. So this telescope will also do measurements with gravitational lensing, but it will look at like a smaller part of the sky, and but will be like more precise, if you want. Like we give more precise measurements of the shape of galaxies. So yeah, there is really an advantage to have space telescopes, and we are going to have some coming in the coming years.
Yes, awesome.
There hasn't, I don't know the answer to this question, but I suspect that the probability has been astronomically small, but there haven't ever been any microlensing events observed with a space telescope, have there?
Not to my knowledge. I know most of the microlensing surveys are like, there's a Polish telescope in at Las Campanas in Chile that's ground-based. I don't know of any. I think it just requires too much observing time that would be better spent by space telescope on individual discrete events. Sorry, did I cut out?
I think we got you.
Okay.
So you don't need to spend space telescope time on it. Okay.
That's my understanding.
That makes sense.
But perhaps you guys have additional.
I mean, I thought the issue was that space telescopes have relatively small fields of view compared to the vast majority of ground-based telescopes. And so when you're looking for very rare events like microlensing, you want as wide a field of view as possible. And so it's really inefficient in most cases to look with space telescopes.
What about something like Kepler or a Kepler-like kind of thing? I mean, obviously Kepler was for doing transiting of planets in front of their stars, but it's just staring at a region of sky for a long period of time to see what's going on there and looking for events. I wonder if that would also be appropriate for looking for microlensing, but again, it's not an enormous field of view. It's reasonably small. I don't know. I'm just speculating.
Yeah, I'm also not a transit person or a microlensing person, so I don't know off the top of my head.
Okay, that's fair. Okay. Well, speaking of space telescopes, what kind of theories will the James Webb Space Telescope speak to? This is a pretty broad question, but I think a few of us could probably speak to it. Mia, do you want to start out?
Yeah, sure. So James Webb is different from its predecessor Hubble in a couple ways. One is I think the biggest difference is that James Webb is really prioritizing the near infrared part of the electromagnetic spectrum. So Hubble was really aimed at the optical with a little bit of UV, but James Webb is aimed at the infrared. And the reason this is important is because infrared wavelengths are longer than optical wavelengths. And when you're studying, for instance, galaxies, or very distant objects, because as light travels towards us, it gets redder. This is the effect called redshift. And so in order to see farther back, we need to be able to look at longer wavelengths, at redder wavelengths. And so that's why infrared is really good. So one of the things that James Webb will be able to let us do is to look back at the very first stars and galaxies. This is the hope, is that we've never been able to look back quite so far. And so we're hoping to find what some of these, the very first galaxies might have looked like. We're also interested in seeing, we'll be able to see a lot more low mass galaxies, small galaxies that aren't as bright at very high distances. And so we'll be able to compare the galaxies that we see today with the small galaxies in the past that were the building blocks for the galaxies like the Milky Way today. So it'll give us a much more direct comparison so that we can start understanding, like piecing together how galaxies form over time. Infrared is also really good because you can actually see through dust in the infrared. So in the optical, like in Cameron's background, for instance, you can see these large black blobs, and that's dust that's blocking all of the optical light. But with James Webb, you'd be able to look right through that dust. And this is really important when you're looking at dusty things like where stars and planets form, because they form in these really dense clouds that tend to be super dusty. And so to understand how stars and planets form, you really want a telescope in the infrared that can see straight through all of that. And then I think the last theme that James Webb is looking at is planets. So near infrared is really useful when you're trying to study planets for a couple reasons. I'm not a planet expert, so the main one that I know is that a lot of molecules tend to have very strong features in the infrared. And so if you're trying to look for molecules that could be signatures of life in particular, so things like water, methane, I don't know other molecules, carbon dioxide, oxygen, those tend to have a lot of features in the near infrared part of the spectrum. And so by looking at spectra of planets with James Webb, the goal is to find planets that are Earth-like and could actually have signs of life. Yeah, so I think those are the four main goals, the four like science themes of James Webb. It's like first light, assembly of galaxies, star and planet formation, and then planet stuff. So that was a very general answer. And I mean, there are also other reasons that James Webb will be really interesting, but I think those are the four sort of main themes that James Webb is looking at.
Just to add, just about, so not exactly the question, but about the telescope, it's a really cool like design, and actually it was assembled all together near Pasadena, like in the LA area at the Northrop Grumman, and I actually got the chance to go see it in real life, and it was like really amazing to see like the gigantic. There's like it's an assembly of little mirrors, like honeycomb kind of thing, and it can like it will deploy once it gets in space, and yeah, it was really impressive.
Yeah, it's super cool, and I guess something that was touched on by Mia, but it's just a very large telescope. I mean, it's really good at collecting a light compared to its predecessors like the Hubble Space Telescope and so on and so forth. So in addition to the change in wavelengths, it's just can see much fainter stuff too, which is awesome. There was a related question that someone just asked about, will Webb and the Nancy Grace Roman telescope, which was previously known as WFIRST, will those just make all these previous telescopes obsolete? And I don't think, I mean, other panelists can speak to this as well, but I don't think it's necessarily that it makes things obsolete. There are a variety of telescopes that we have, both ground-based as well as space-based, and they have a variety of different like eyes on the sky in terms of their ability to see a wide region or a narrow region or different wavelengths of light or different, having a coronagraph so you can block the light from a star and see the planets around it. There's lots of different things that you can do. So no, I don't think it necessarily makes all of the previous stuff obsolete, but a lot of this stuff works together. The different data sets,
Yeah, and especially since there are so many astronomers that want to observe so many things, and the sky is huge, right? So there are only so many 10-meter class telescopes, and there are many more 1-meter class telescopes. So there are way more observations taken with the smaller telescopes than with the bigger ones.
Yeah, so maybe to give a sense of scale, the Hubble Space Telescope is, one of the premier NASA flagship space telescopes. And I think the oversubscription rate, so when you apply as an astronomer, if you're interested in observing, you have to apply to get time on these telescopes. You have to write up a proposal about what you want data for, why it has to be this telescope, how long you need it for, and you have to make a case, like why is this science worth it? And the oversubscription rate, there are tons of really amazing proposals and really great ideas, but only 1 out of every 10, or it's more than that, it's like 1 out of every 14 or something, proposals actually gets time. And so that means there's already 13 really great science ideas for everyone that Hubble actually manages to look at. There's 13 other ideas that Hubble just doesn't have time to look at, and that a committee has to decide, well, we can't do this right now. And so having more telescopes is definitely better for getting more data. As an observer, it's always great to have more options.
Agreed. Okay, let's see. There's a question that we had from one of the audience members referring back to when we were discussing the SpaceX, Starlink, and the various different satellites. And that is, any thought for the debris that so many satellites could then collide or something like that? So this is a theorized bad situation that's awaiting us called the Kessler syndrome, where you have enough satellites in space that are flying around. Space and the orbit around the Earth is large, just like the surface of the Earth is quite large, that when you have a handful of things whizzing around, the chances of them colliding are pretty small. But when you have tens of thousands of these objects flying around, and they're whizzing at, thousands of miles an hour, then the chances of them impacting each other becomes increasing. And the concern is that once you have a couple of collisions which create many fragments of many smaller pieces, a screw from a satellite flying off that way and a piece of shrapnel flying off that way, it very quickly goes nonlinear, and you have all of a sudden this cloud of debris surrounding the orbital space around your planet, and anything that gets caught in there is going to get hit by one of these whizzing pieces of shrapnel, and that's going to cause another explosion, and it's bad. It's bad for the satellites that are going to get destroyed, and it's bad for people who are trying to send things through that cloud of whizzing debris, whether it's astronauts or rocket launches that don't have any human payload on them or whatnot. So it is something that people are concerned about, but right now it doesn't seem like like many of the problems that our civilization faces, it's kind of a tragedy of the commons sort of thing. No one wants to be in charge of picking up the litter that's out there or fixing the problem because they don't get anything out of it. It's not profitable. But it's going to be everybody's problem if we don't self-regulate. So yeah, it's a concern. You addressed a very relevant and pressing concern that we're all facing in the next couple of decades. But to my knowledge, no one's really doing anything about it. And it's hard. It's a hard problem. How do you pick up a bunch of litter of dead satellites that are hanging out up there, or have some global library of satellite orbits to make sure that people aren't running into each other, especially when half the satellites that are up there are classified by various governments to spy on the surface of the Earth. It's not good. Sorry, I know my internet's cutting out again. Crap. Anyway, it's bad. I guess that's all I have to say. It's bad. You guys want to add anything about the Kessler syndrome? No. Okay. Let's see. Additional questions. Here's a question from Mia. Is the chemical composition of small galaxies different from larger ones? Have they had different kinds of stars generating less or more of some specific elements?
Yeah, so on average, there's something called the mass metallicity relation. There's a relationship between how massive a galaxy is and how many heavy elements it has. And in general, more massive galaxies have more heavy elements. And so this is for a couple of reasons. One is because of inflows and outflows of gas. So when when stars explode and when they live and they die, they produce winds, they produce energy and momentum that they release into a galaxy. And some of that energy and momentum can actually push out some of these heavy elements. And it's more likely to do that in a less massive galaxy because the smaller galaxy doesn't have as much, as deep of a gravitational well. So it can't hold on to its metals as well. So that's one reason that we see this mass metallicity relation. The other is that typically smaller galaxies tend to be pretty old. This is not true for all dwarf galaxies, but many dwarf galaxies tend to be old in the sense that were basically formed from a relatively short burst of star formation and then nothing after that, or very little star formation after that. And so they don't really get a chance for those early generations of stars to produce metals, to produce heavy elements that later generations can use. Whereas in more massive galaxies like the Milky Way, there's basically constant star formation. So there's constantly stars producing heavier and heavier elements and releasing them back into the galaxy. Does that kind of make sense? So that's one of the main reasons that we see this difference. And then, as I mentioned earlier, the second question was about, do different kinds of stars generate more or less of different elements? The answer is yes. And I talked a little bit about this when we talked about reticulum-2 earlier, and how reticulum-2 has more of these R process elements that come from very rare events, and we think neutron star mergers might be one of those events. But other things, like we think that elements like magnesium tend to come from the deaths of really massive stars, whereas things like manganese and nickel and chromium, those tend to come more from the deaths of stars that are more like our sun. After our sun dies, after our sun runs out of fuel, it will eventually become a white dwarf star. And sometimes those white dwarfs explode. And that's a different kind of stellar explosion that produces different kinds of elements from the explosion of a massive star. So, and in some cases, yeah, there's overlap in some cases. So for instance, in dwarf galaxies, you can get a lot more type of these white dwarf explosions than this supermassive star explosions, especially after the star formation sort of stops. And so you do get different patterns of different elements in these galaxies. Yeah, that's a great question. I mean, there's an entire field called galactic archaeology, which is what I do, which is really about looking at the composition of stars in galaxies and trying to use those to figure out what kinds of events happened in the past in those galaxies to make those elements. So yeah, it's a whole subfield. It's really cool. If you're interested in learning more about it, strongly recommend.
Yeah, and in fact, Mia was one of our previous speakers this spring. So I encourage you guys, if you look below on our YouTube channel, you can find our past events from the Stargazing lecture series. And I think, Mia, you spoke in May, was it? Maybe June?
Yeah, I think it was May.
Yeah.
It wasn't quite on galactic archaeology stuff, but it
That's
was sort of similar about the chemical composition of some galaxies.
exactly. So that's good viewing background for those of you in the audience who are interested in more on this. Okay, I about out of time, to be honest. Do any of the panelists have any parting thoughts for our audience? Anything that they really want to convey about science, space, the world? Remember to vote. For those of you who have the opportunity to vote in advance, I encourage you to do so. I'm going to be a poll worker. I'm very excited about that. Hopefully I don't catch any kind of COVID whilst doing so, but we will see. Yeah, I guess we'll just end it there. Thank you to our wonderful speaker, Agnès Ferté. That was wonderful. Excellent presentation. Also, many thanks to both Mia and Leo. Mia has relocated to North Carolina, so it's midnight for her right now. She stayed up talking about science on a YouTube live stream until midnight, even though my internet keeps cutting out. Leo is in Mississippi, so he stayed up quite late as well. Thank you to our audience members for the wonderful questions. Again, our next event will be an Astronomy on Tap a week from Monday. I don't yet know who the speakers are, but I'll put it online as soon as I do. And our next stargazing lecture will be in a month, given by Dr. Katie Bauman, who will be talking about black holes and the imaging of the black hole, both hopefully soon, Sagittarius A star, the black hole in the center of our galaxy that was the research on which was given to Dr. Andrea Ghez and Dr. Reinhard Genzel for the Nobel Prize this week, but also a supermassive black hole in a nearby galaxy, M87. So yeah, exciting things in the future. We've got an Astronomy on Tap coming up in the next couple months. That'll be the science of Star Wars versus the science of Star Trek. I'm very excited about that. So anyway, thanks everybody. Stay safe. And we'll see you guys in a couple weeks. And thank you, panelists.
Thanks so much.
Bye.
Thank you. Bye.
Okay, our stream is ended.